Hello and welcome to York University Astronomy and Astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. You will now find us wherever podcasts are distributed. I'm Paul Mackin, one of your hosts this evening, and I am joined by Professor Mary Helen Armour. I will apologize in advance. I'm fighting a bit of a spring cold, so if I suddenly get in trouble, I'm sure the good professor will immediately leap in and rescue me. We are both affiliated with the Department of Physics and Astronomy here at York University. Tonight, we're broadcasting live from the Allan Carswell Observatory on the Keele campus of York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday at 9 p.m. local time, or currently 1 a.m. Toronto Universal Time, Tuesday Universal Time at York U Observatory. We also run in concert with our online public viewing, or as we call it, the OPV, feed, which is run by the observatory staff, where, and there's questionable skies this evening. We won't have the domes open, but we will be sharing some wonderful archival images and answering any questions you may want to type in on YouTube chat. To navigate to our live show or to find out more about us, please check out the website at yorku.ca/science/observatory and follow the link to our online public viewing chat on YouTube. Any questions or comments you may have on past shows or suggestions for future topics, please send them to us at observe@yorkuniversity.ca. You can also connect with us on Instagram with the handle at YorkU Observatory, or on Facebook at Allan I. Cars Web Ob. All of our programs are free, but if you'd like to make a donation, and we would certainly appreciate that, please see our website at yorku.ca/science.observatory. We'll be monitoring the YouTube chat for questions and post content as we go on. So, happy Easter, everyone. How are you this evening, Professor?
Oh, pretty good. I think I'm fortunate in that I've gotten over all my spring colds. I've had my round of them a couple of weeks ago.
It sort of came out of the blue on Saturday night, and I think it's at the sort of declining, just crossed the hump from the ascendancy to descendancy, but a little bit further to go. Are you looking forward to the end of term and the Easter break?
Well, the end of term is usually extremely busy for professors.
Yes, and for students, I will add.
Yeah, so it's I think it's when you get to the end of like April, first week of May, and things slow back down again.
Start to calm down. Yeah, my heavy side date is the 21st of April with my quantum exam this year. So yeah. So my family doesn't actually celebrate Easter, and I've always found it among the most confusing of the sort of Western religious holidays. Perhaps, Professor, you're really good at this date stuff and how it all fits in the astronomical calendar. Can you enlighten me a bit?
Why do we have Easter where it is, and why does it move around? And it's a similar kind of process for the Jewish Passover. So what happened is, back in what we refer to as the Dark Ages, the church decided on how they were going to date Easter, and Easter was placed. So it was the first Sunday after the first full moon after the vernal equinox. So this year, the vernal equinox was March 20th. So it was a little early. It varies by about a day or so, somewhere between the 20th and the 21st. The full moon is this week. It is April 2nd. Right. And so after that, we have Easter, then is April 5th. Right. And it's very interesting because, this dates back. This is one of those councils a long time ago. I don't remember exactly which one sent the date of Easter. But what got to be really interesting is, by the time you get to the 1500s, an important part of how you set dates was figuring out when the equinox was. So the Catholic Church always had a certain number of astronomical observers. So what was happening by about the 1500s is, of course, because you had the Julian calendar, you didn't have leap years. So the equinox was slowly moving through the calendar. And the church was rather, I guess, upset by this, and they wanted to pin it down more. So what they ended up having to do was figure out sort of more the exact length of a year. And they called, I think it was the Council of Trent in the 1500s. And this went on for several years. And it was under Pope Gregory that a new calendar was established. And this is when we added leap years to the calendar. And so ever since then, every fourth year is a leap year, except the century years. But every fourth century, so in 2000, we had a leap year, but in 1900, we didn't, and in 2100, we will not. And this fairly well accounts for the actual length of the year, and it keeps the equinox around March 20th, 21st, rather than having it sort of slowly move through the calendar because you're not taking into account the leap year. And this is why it's called the Gregorian calendar, because it was Pope Gregory 10th, 12th, I don't know, one of them, who is the one who established this calendar. And probably at that point in Europe, at least, this is sort of, right around the time of the Reform and Protestants and stuff. But he was still probably one of the few people who had the authority to force most people to switch calendars. In England, it took them, eventually they acknowledged that the Gregorian calendar was just a better system and they switched to it, but they did not switch right away. Russia did not switch to the Gregorian calendar until after the Russian Revolution. So their Julian calendar, the joke is the sort of November Revolution actually, or the October Revolution actually happened in November, because they were still on the Julian calendar and everybody else had pretty much moved to the Gregorian in sort of Europe and sort of the Western world at that point. But the Gregorian calendar, the real driver to create this calendar, our current calendar that we have, is actually because of the church wanting to keep Easter in particular pinned to the same time of the year. Because otherwise, in theory, if the equinox kept moving, if you keep Christmas the 25th of December, for example, another major religious holiday, and there were many, many others, if the equinox kept moving, Easter would start moving into other religious points in the calendar. And eventually, time passes, Easter and Christmas would actually be very close together, which is not what they wanted. So the dating of Easter is really what was one of the major drivers in our current Gregorian calendar. So it ties in a lot of interesting ways. The other really ironic thing is the people who were putting together the Gregorian calendar actually relied fairly heavily on the work of people like Copernicus, despite the fact that a few decades later, they would ban his work and declare it a banned book. So there was a certain amount of hypocrisy on the part of the church because his work and his calculations had to actually be used in order for them to create this accurate Gregorian calendar, right? So there was all kinds of weird stuff that went on there around that kind of time period. But our modern calendar does stem, at least in part, from the dating of Easter. There were other things that came into it, but that was one of the major drivers between updating from the Julian to the Gregorian calendar that we now basically use in the Western world.
Yeah, it's interesting. It was actually Gregory the 13th.
13, yeah.
Quickly looked that up while you were. Yeah, I think I looked it up while you were chatting, and I was coughing. But of course, there are still I have friends who are Greek Orthodox, and my part of my wife's family is Ukrainian Orthodox. So they still use the Julian calendar, which is why their Easter can be in a different time, and certainly their Christmas is usually in January and so on. So it's still the Julian calendar is still used, not not in any sort of commercial sense or in a day-to-day sense, but for religious holidays. It still is used in certain parts of the world. But Easter aside, my favorite thing about this time of the year, other than chocolate, I must admit I have a weakness for chocolate, so Easter's good. But my big thing at this time of year is galaxy season is upon us, and this is the time of year when, if you look into the east after sunset, galaxies start to rise up and in the east. And now, none of these things are visible really to the naked eye. If you had very clear skies, a couple of them you might sort of see little dusty patches, but they are visible in binoculars. But this is kind of a telescope thing. So here are five targets for even a small telescope. We'll talk about telescopes in a bit. So the first one is a favorite of mine, and it's actually in our calendar this year, and it's the May. I think it's actually the April. Uh, it's the April issue, so April month. So you can if you've got our calendar, you can look it up, and if you haven't got our calendar, still time to get it. There's more than two-thirds of the year left to go. But it's the Leo triplet, also known as the M66 group. So this is a small group of galaxies in the constellation of Leo, and they're about 35 million light years away. It consists of M65, that's Messier 65, Messier 66, and NGC 3628. Very striking. They're all spirals, but they're all at different sort of angles, and you can see different features about them. So it's really very cool to see. Another one of the sort of more famous, and there's a lot more than just five. Galaxy season, it brings you a plethora of observing opportunities. But the Bode and the Cigar Galaxy, M81 and M82. So M81 is Bode's galaxy, and it's approximately 11.8 million light years from Earth. M82 is known as the Cigar Galaxy, and it's an irregular galaxy. Bode's is a spiral. About the similar distance. And M81 is about 2.5 times more massive than M82, which has definite influence on how they interact. Both galaxies are ideal for viewing with binoculars or small telescopes, so they're definitely not visible to the naked eye. And they're in the Big Dipper. So you can, any star chart will point you towards them. Now, one of my personal favorite is the Pinwheel Galaxy, or Messier 101. It's a beautiful face-on spiral galaxy, also located in the Big Dipper and Ursa Major. It's 21 million light years from Earth, and there's a very famous picture of it released by NASA and the ESA using the Hubble Space Telescope, and you can look that up online. But it is very detailed, very gorgeous, and it was one of the first. It was one of the first images that NASA used to try and calibrate the Hubble Space Telescope, and that's when they found out it had problems, and they had to install basically a set of corrective lenses on it, and then we got the benefit of those and great images. Another really beautiful one is the Whirlpool Galaxy. This is actually a pair of galaxies that are interacting gravitationally, and you can see matter, a matter bridge between them, like star bridge between them. But it's again a face-on spiral galaxy, got a very bright core, sweeping spiral arms, and it's got this close interaction with its companion galaxy. If you take a look at the page for this podcast, there will be an Easter picture, and that is showing M51. And finally, and this one's not quite as spectacular, and it's a bit smaller, so you can see it even in modest telescopes, but it really starts to get amazing in the larger scopes, is M104, the Sombrero Galaxy. And again, there's an iconic photo captured by the Hubble Space Telescope, and this is what's called an unbarred spiral galaxy. So it is spiral straight across. There's no central bar to it, uh, and it's located in the constellation of Virgo. Now, in terms of how to observe these, well, they're not naked eye objects, as I said. You need to at least binoculars or a small telescope, and if you don't have access to either, find an astronomy club or an observatory, such as ours, the Carswell Observatory, near where you live. They, like we, often have observing nights, and you can check these out. Also, if you're in the market for an inexpensive telescope, you might consider one of the new smart telescopes. You can't actually look through these. They actually interact with your phone or your tablet and produce images live, but they don't have an eyepiece per se. And that's actually, in some ways, a bit of a better thing because sensors can gather more information than your eye can. But they go between like $400 and $800, which is reasonably modest for a telescope. And you'll find these objects, these telescopes, you set them up, which is trivial. Um, you basically grab your phone, open the app, tell it what you want to take a picture of, and it will take images directly on your smartphone. They're inexpensive, easy to use, and very powerful. And actually, our Christmas show, which was at the beginning of December last year, we actually had a bit of a buyer's guide for telescopes. So if you're interested, you can go back and maybe listen to that part of that. So, saying all that, I mean, Mary Helen, do you ever partake in some galaxy season observing?
I because my research is more in the area of geophysics, I don't do a lot of normal observing. I'm more of a data analysis.
Right, I got it.
Strangely enough, for an astronomer, I've never owned a telescope of my own. I did do my master's in physics and astronomy, and it was just not. I was the one, like, I loved all the CCD images and lots of data and process it all. And you look through the telescope, you're like, yeah, okay, it's much cooler.
Yeah, looking through, I only remember a friend of mine years ago. I showed him an object in a telescope. I think it was M57, and he was remarkably underwhelmed. And that's when I learned the important lesson that looking through a telescope, if you know what you're looking for, it's great. But if you don't, looking at data from a telescope is far more interesting. But anyway. So, on to this week in astronomy and history. Mary Helen, I think you've got something to tell us about an
Yeah,
asteroid.
so it's like I said, just because I've always been interested in impact craters, I'm always interested in the objects that make them. So actually, in the early 1800s is when they started to discover asteroids, and it was in late March that both Pallas and Vesta, the second and fourth one, were discovered. Um, so second Pallas 2 was discovered, I think it was around March 27th, 1802, by an astronomer by the name of Olbers. And about 4 years later, around the same week, around March 28th, he also discovered Vesta. Now, of course, if you follow any of the space news, we did actually send a probe to Vesta, and it found a lot of really interesting results about this asteroid. Pallas and Vesta, obviously, since they are some of the first ones found, are also two of the very largest. Ceres would be the largest, and it's big enough we now consider it a dwarf planet. These next two are still more potato shaped. They're what we more truly think of as asteroids, but Ceres and then sort of these two within a couple of years, because Ceres was about 1801. The discoveries over these first few years of the 1800s is what really led to people starting to look for more asteroids. And this is how we sort of discovered the asteroid belt with, finding these first few. Another thing that always fascinates me, of course, is comets. And one of the comets, of course, that everybody's familiar with is Halley's Comet. And, some people are aware of it, having been visible in the sky around 1066, which of course is when William the Conqueror knocked off Harold in England. but it has been seen much earlier than this. And the earliest sort of well-documented sighting was actually about March 20th, 240 BCE. Okay? And this was by Chinese astronomers. So Halley's Comet has been sort of coming back to Earth for at least 2,000 years at this point. And this is sort of the earliest record we have found of Halley's Comet in any of the astronomical records. Halley was working on ones that were much closer to sort of the 1700s when he was working. But when we start tracking back through the records, we can see that we have recorded Halley's Comet coming back over and over and over again, literally for thousands of years. If you sort of, start looking through some of these, astronomical records that are actually detailed enough that we can trust the dates like this. So Halley's Comet's been seen quite a lot of times through the past. But these were all sort of those smaller solar system objects that are much harder to see. But in that sort of time period, 16, 17, 1800s, the discovery of all these smaller objects sort of really changed our understanding and sort of our view of what was going on in the solar system. So, but I think you have some much more recent history to talk about, and probably something a lot more relevant to some of our current activities that are going on.
Well, I will make a comment that the mission that visited, you mentioned 3 asteroids. You mentioned Vesta, and you mentioned Ceres, and you mentioned Pallas, and Pallas and Vesta were both discovered around this time of year. Ceres being the largest, but the spacecraft that visited Vesta was a bit unique in that it was given, and we will come back to this theme perhaps a little later, an ion propulsion system, which basically allowed it to go not only to Vesta, but it then went on to Ceres, and that was the Dawn spacecraft. And the idea behind an ion drive is that it will allow for, it's low thrust, but it's high specific impulse, and you can get of using very little fuel, you're able to move the spacecraft, and you're able to turn this engine on. If you think how a rocket works, you turn the rocket on, and 8 minutes later you're in orbit. You burn through a whole bunch of fuel. Well, they can turn on an ion drive and use not very much fuel, maybe 100 kilos or something, for 3 years. And that's how they were able to go first to one asteroid and then on to a second one. So that sort of brings us up to, the kind of modern era. But we are investigating these objects. There's always ongoing missions to asteroids. A lot of interest, always a lot of interest in comets as well. But for my history item, not quite 56 years ago. So it was sort of April 11th, but from April 11th until April 17th, 1970, this was the last manned mission to travel out to the moon, go behind it, and head back as quickly as possible to Earth. This was crewed by Jim Lowell, Jack Swigert, and Fred Hayes, Apollo 13. And it was considered NASA's successful failure. And this story is captured in a really good film of the same name, starring
Tom Hanks.
Tom Hanks, yes, Tom Hanks, and directed by Ron Howard. Yes, but an excellent film. So it was planned as the 3rd manned lunar landing. The spacecraft successfully launched, but on the 13th of April, an oxygen tank exploded, which effectively destroyed the service module. Now, the Apollo spacecraft stack had 3 modules. It had the service module, which was basically life support, power, and propulsion. Then it had the command module where the astronauts lived, and then it had the lunar module. Well, no service module, so that left the crew without power and life support. uh, uh, and electricity. So they had, no power. They were in real trouble. So they used the lunar lander as a lifeboat. The crew to change the trajectory of the spacecraft to what was called a free return. So they just swung around the moon and headed back to Earth. Now, there were a lot of problems to solve. Uh, Biggest among them, the LEM was designed to keep two people alive for 2 days on the moon, and they now had to get three people back to Earth in 4 days. They struggled with issues of power consumption. They had a problem with CO2 buildup in the atmosphere of the spacecraft. It was incredibly cold. They had limited crew rations. One of the crew members became sick on the way back, quite sick. Um, Even as they worked through these problems, they didn't actually know if the command module, which was the part that was going to have to re-enter Earth's atmosphere, was damaged in the explosion. And if it had been, it would have been the heat shield that was damaged, which would have been disastrous. So this was a really heroic effort. And the NASA team developed a motto for this mission, which is failure is not an option. And the crew did make it back successfully. It proved to be NASA's finest hour. And I was talking about this earlier. And if you've ever seen the movie The Martian, there's a scene in there where they're trying to capture the astronaut trapped on Mars. And there's the scene where people are in Times Square and they've got big screen TVs up. And that is actually a historical reference because that's exactly what happened with Apollo 13. It was a mission that nobody was interested in covering. We'd already been to the moon twice. We'd beat the Russians, quote unquote, boring. And then suddenly this happened, and the whole world got engaged. And I'm of an age that I can remember this. I remember waking up one morning and listening to CBC radio, and this had happened overnight. And it was, I was excited because I was into that sort of thing. I was very excited about the mission to land on the moon and whatnot. And I suddenly heard that they weren't landing on the moon and they had to come back. And I remember feeling profound disappointment and then real fear that these astronauts couldn't get back, but they did it. And it's just an amazing story.
Oh yeah, I mean, even if I mean, there are liberties taken in a movie. There have to be to get the whole story into 2 hours. But if I'm too young to have remembered it, um, but as like I said, my dad in particular has said like everybody's like glued to their radio and their TV trying to figure out what was going to happen because this was sort of uh, played out on TV in a way I think too that something like this had not happened before. Like now we kind of take it for granted. We watched the Iraqi war and Iran and all these things, and you see it almost in live time, and people are a little bit jaded. But to have this kind of thing and to have it running live on the news, again, it was something that just hadn't been seen before. So it was in a cultural way, it was sort of a unique situation too, in a first, because prior to this, you just didn't have that kind of real-time news or real-time communication, where you could sort of see these things happening, and know about it almost immediately.
Yeah, I mean, it was world shaping. I mean, the lunar landing itself on Apollo 11 was a big deal. A billion people watched it, and that was at that point a quarter of the world's population. But Apollo 13 just captured the world somewhere between wonder, terror. It was a remarkable event. And as I said, I remember it. And we actually got in our classroom, I was in grade four, I guess, or five. Yeah, probably grade five. And I remember them wheeling a TV into the classroom, which never happened. So we could watch the reentry and landing. And it was the whole world was completely galvanized. It's just a remarkable story. But we're going to come back to this story in a second, or in 20 minutes or so. But saying that, we're at the halfway point. So time for A couple of things. First of all, I'm going to say that we are listening to York Universe, the Space and Astronomy podcast from York University. We're broadcasting live from the Allan Carswell Observatory at York's Keele campus in Toronto, Ontario, Canada. You can look at our website at yorku.ca/science/observatory to join the chat if you have any questions or want to see some of our content. We've also got our OPV going on, and right now we're looking at a couple of images, including M57, which I mentioned a little while ago. And of course, there's a live chat there. Any questions you've got, you can type them in there, and our team will do their very best to answer them. I also want to talk about tours. We've got a tour every Wednesday. Our next tour is April 1st, and I'm not fooling.
Paul, just to be clear, there isn't
Oh,
actually a tour this week. The next
oh,
one is April 8th at this point.
April 8th. Okay,
Yeah.
I guess I was fooling. So sorry, I didn't get that. So there's no tour this week. So April
No.
8th. And these tours are a lot of fun. If we're live, if the night is clear, we have the domes open. You'll see us live image. You look at it on a computer screen to see what we're looking at. And you get to see our 60 centimeter scope and our 1 meter scope and meet the team. They're a lot of fun. They're free. You just have to go to our website online for your free ticket. And Mary Helen, you were going to talk about the astronomer
Yeah.
in residence.
Yeah, and just a quick note about the tours over the winter because of weather and stuff. We just do tours of the observatory, but starting April 15th, we will also be starting our arboretum tours where we have, instead of going into the observatory, we have a space on top of one of the parking garages where we have a number of smaller telescopes that people can look through, and we do some sort of real observing and description of the night sky. So those will also start April 15th at this point. The other thing, of course, we have going on over the summer is what we call astronomer in residence. So for 4 years now, maybe it's 5 years, we have had a joint project with the Killarney Provincial Park. And so what happens is the various sort of astronomers associated with the observatory, sometimes it's grad students, sometimes it's professors, sometimes it's some of the amateur astronomers who are involved with the observatory. And they will go up there for a week at a time, and they'll do 2 or 3 presentations while they were up there during that week, because of course Killarney Provincial Park is a dark sky preserve, so the visibility of stars and other objects up there is amazing. Right? So if you are interested in doing this, there is an application for this on the York Observatory webpage. So if you go there and you see sort of astronomer in residence, you can click and go and you can apply. On the other hand, if you're going up to Killarney Park this summer, for most weeks between sort of sometime in June to well into September, we usually have the odd person will be there in May. Sometimes there'll be someone in October, but particularly in sort of the busy camping months like June, July, August, most weeks there will be an astronomer up there who does some. We usually do talks. We do sometimes it's solar observing, sometimes it's observing at the. They have a 40 centimeter telescope, 16-inch up there. So it's quite interesting. And whether you're an amateur astronomer and you think it might be interesting to go up there for a week and do this outreach, or if you're a member of the general public, this is definitely something that's worth seeing while you're up there at Killarney. So it is a great project. So that is what we call our astronomer in residence program, and it's a great experience whether you're doing the outreach or you're a visitor to the park, because the seeing in Killarney is pretty amazing. I was up there the last 3 years running. I am not going this summer, but it is a great place to go to do observing. So have you ever been up to Killarney, Paul?
I have, but not as part of the astronomer in residence program. But I've been to Killarney Provincial Park. It's a wonderful location. I mean, it's like a good chunk of Ontario in this northern Ontario in the summer. A lot of mosquitoes and flies, but we've got technology does a good job taking care of that. So it's and the skies are second to none. They're all Boreal too, and it's just phenomenal. They're yeah, I may go up this summer, but again, I wouldn't go as part of the astronomer in residence program. I just go up and take one of my telescopes and camp for a week or something. So we'll see. Um, Moving on to news, uh, Artemis 2 is launching on April 1st. Again, no fooling, although it could be delayed to April 2nd. Right now, they're showing an 80% probability of okay weather at the launch site. So, assuming there's there's been a couple of scrubs already. And assuming there's no further scrubs, this mission will launch on April 1st. And I mentioned Apollo 13 a little while ago, the last manned mission to go around the moon but not land there. This is now the next one. Very different circumstances. Apollo 13 was supposed to land, and this one's not supposed to land. Um, but it'll be the first crewed flight to the vicinity of the moon since Apollo 17. Very different mission profile. It's carrying four astronauts on a 10-day journey. It's part of the Artemis program, which has been rebalanced a little bit to focus more on the moon and less on Mars, but it's still got Mars in the plan a little bit. This mission is a test flight for the Apollo spacecraft, for the Orion spacecraft, and the Space Launch System rocket. Um, the mission will, as I said, not land on the moon, but the crew will experience deep space, test life support systems, navigation, and communications. So the crew is three NASA astronauts: Reed Weissman, Victor Glover, and Christina Koch, and Jeremy Hansen, who is a Canadian astronaut. And that's very exciting for us that one of our own is going up there, and he's a keener. It's very exciting. So the mission is again on a free return trajectory. So once it's pointing in the general direction of where it's got to get to, which is the moon, it doesn't point to the moon. It points to where the moon is going to be in a few days. And then it just goes out there and loops around the moon and comes back. Basically, once it's going, aside from course corrections, Isaac Newton is driving the spacecraft. Um, so this is a safe, non-risky trajectory. Basically, they don't have to go into orbit. They don't have to fire up the engines to come back and so on. So they're going to be testing systems. They'll validate the Orion spacecraft flight support system, navigation, and communication capabilities in deep space. And they're also going to try out some optical communications to and from Earth using lasers. It will be a distance record. Excuse me. Artemis 2 aims to go further than it'll be the furthest humans have ever traveled from Earth, going approximately 7,000 kilometers behind the moon. So the mission plan is it will launch, and then there's two solid rocket boosters, and then and the core four engines on the SLS. It will launch. It will take off. The boosters will separate at approximately 4,800 kilometers up. Then they'll get the core stage will burn for about 8 minutes, and then it will leave Orion in a kind of an odd elliptical orbit. What happens is they get into this orbit and they check out the system right after the main cutoff switch. Koch and Hansen will unstrap from their seats and set up and test the essential life support equipment on the spacecraft, including the water dispenser, which they need for drinking and for making food, firefighting masks, and the toilet. Because you do not want to go all the way to the moon with four people in a very cramped space without a working bathroom. Once all the systems are checked out, then the upper stage of the SLS will reignite, and it'll raise the spacecraft's highest point. and sorry, the lowest point. And then if they didn't do that, the spacecraft would automatically return to Earth. So there's a lot of safety built into the mission planning. So it then boosts the ship so that its next apogee is about 70,000 kilometers. It's a 23.5-hour Earth orbit. Uh, so after that, they'll move into, they'll basically do some more, they'll do some docking simulation with the upper stage of the SLS, and then they will back away and test their engines a bit on their just the Orion spacecraft. And then they'll sleep for a period 4 hours, and then they'll wake up, and then they'll do another burn, and they'll sleep again, and then they will do a translunar injection, which is the burn that's going to put them en route to the moon. They're heading off to the moon. It takes about 3 days to get there, but it's what's called a free trajectory, as I said. So once they burn, they're automatically going to come back to Earth anyway. They do a lunar flyby. Then after the flyby, they're going to use the moon's gravity to return to Earth, and there'll be some uh, trajectory corrections on the way back. And then they'll do a reentry and splashdown, very similar to what Apollo used to do. It'll enter the Earth's atmosphere at about 40,000 kilometers an hour. And this is the fastest reentry ever attempted. And it's not going to just come into the atmosphere. It's going to use what's called a skip reentry. So it dips through the atmosphere, skips back out into space, which causes it to lose some trajectory, and then comes back into the atmosphere and uses the atmosphere to slow it down, eventually firing its parachutes, and it will land in the Pacific Ocean near San Diego, and the U.S. Navy will recover it. And the mission is expected to last about 10 days. And this is a big deal. I mean, there's some things about this mission that are a bit weird. The SLS is really obsolete technology. When you look at what SpaceX is doing, able to land spacecraft, and the New Glenn from Blue Origin is able to do the same thing. But it is a big, really big wampum rocket. And this is going to be very impressive, and it's going to be so great to see a Canadian and three NASA astronauts, not to sell anyone short, go all the way out to the moon. Are you going to be watching it, Mary Helen?
Possibly. It
Maybe.
depends on how it fits around all the other things I have to do in the day.
Yeah, I hear you. Well, it's not. If it launches April 1st, it's launching late afternoon, Florida time. Uh, if it launches April 2nd, 3rd, or 4th, it will launch in the evening. You'd have a nighttime launch, which would be pretty spectacular as well. So, Mary Helen, news. You've got something on. You've got something in the news as well.
Yeah, so I'm going back to my planetary theme. So here I was looking. I read through the American Geophysical Union, and actually they're a good journal to read because they've got one journal called EOS that does a lot of basic science and sort of brings sort of new discoveries. But they also have a couple more advanced journals. And I was sort of reading through a bit of stuff, and I popped up in the last day or two this really interesting article about Jupiter, and this was just published recently. Now, we've always kind of known that Jupiter has lightning, but it's only sort of recently that they've been able to get a much better estimate of how strong this lightning is. Juno had been trying to sort of do this, but one of the problems is that you get so many bolts at the same time. It was impossible to kind of differentiate and tell them apart. So they managed to find a bit of a more isolated storm using Hubble, actually, and then they got Juno to look at it. And they found out that lightning bolts on Jupiter are at least 100 and up to, they figure, as much as 10,000 times stronger than the ones we have here on Earth. So that is a massive amount of energy. To put that into perspective, when you get to these really big bolts, you are starting to approach the kind of energy you get in a nuclear detonation. So just massive, massive amounts of energy. And lightning bolts are quite interesting because of the way they interact with the atmosphere. So on Earth, when you have a lightning bolt, of course, it goes through our nitrogen-rich atmosphere and it produces nitrous oxides, which, although we think of them as quote unquote air pollution, when they fall to ground and they hit the rainwater and they fall to ground, this is nitrous oxide and it brings nitrogen into the sort of plant cycle, right? So lightning bolts are actually, in a way, a way to create fertilizer, because the sheer energy of the lightning causes these chemical reactions, produces nitrous oxide. These get trapped in rainwater. The rainwater comes down, and essentially you're adding nitrous oxides to the soil, which is, a form of fertilizer. Now on Jupiter, they've been looking at it because, of course, Jupiter's atmosphere has a bit of a different chemistry. But when you look at a lot of the chemistry going on, one of the very important things is these lightning bolts are a major contributor to the energy that's driving a lot of chemistry in Jupiter's atmosphere. So it's quite a fascinating thing to look at these because of the chemistry they trigger. They do think sort of early lightning strikes, even on Earth, may have played a role in the origins of life. So looking for lightning on other planets, it's not just about, okay, understanding storm systems and the strength of storm systems. There's also a lot of chemistry that goes on that potentially has biological links, right? So this is sort of one of the things they've been able to do at Juno. Now, one of the unfortunate things is Juno has been there for quite a while. It's been extended a number of times because if it's already there, it's cheaper just to keep it running than to worry about another one. Unfortunately, the way NASA is going, due to budget cuts, Juno may end up being just terminated or abandoned. You would hope they would, crash it into Jupiter or something so it doesn't end up, somewhere unfortunate, like crashing into Europa, where heavens knows what kind of interactions it could have. But it's kind of unfortunate because Juno may be getting to the end of its lifespan. But this is yet one more sort of fascinating discovery that has come out of this mission. So, like, to get this better understanding of the lightning on Jupiter and then sort of look at the chemistry and everything it drives is really quite fascinating.
Yeah, I remain hopeful they'll extend it. What NASA has done, even in times of budget cuts, is they have successfully managed to allocate continuing missions because all the sunk costs are gone. It's just operational, so they get more bang for the buck from those missions. I'm not saying they will do that, but I know there's a lot of lobbying going on to get this continued, and the U.S. space lobby is robust. So groups like the Planetary Society and whatnot are really pushing for
and
this.
let's be honest, people like JPL and stuff are also tied to the defense complex, which has a lot of influence. So there's some of
It
that as well.
absolutely does. Yeah,
Yeah,
it absolutely does. Speaking of big missions, though, we've talked about this several times, the Vera Rubin telescope, but it's now, we're going to continue a story from a couple of weeks ago. They're now in science operations. So there's a bit of background. It's located in Sierra Pachon in Chile, and it's got a very dark sky there, dry conditions. It's a desert. It's a mountaintop in a desert. It's a very large telescope, 8.4 meter telescope. It's got a 3.2 gigapixel camera, and it's got a specific mission, a 10-year legacy survey of time and space. It's going to map the entire southern hemisphere every few nights, generating 20 terabytes of nightly data and issuing alerts for transient events every 60 seconds. So, this is a revolutionary workflow. Basically, the idea here is it looks for things that have specifically changed. Okay, it's science goals. It's got rapid imaging. It's got a data pipeline. It's actually got several data agents that are responsible for shunting data to certain particular ways. An example might be a supernova is detected. Within a minute, that information is sent off to the Gemini observatories, and they can train a specialist instrument on to that site and get data about a supernova, because a supernova can be gone very quickly. Similarly, if they find an asteroid, they may want to send it to basically some of the Earth defense organizations out there to make sure it's not going to hit us. I will say that the dinosaurs didn't have Vera Rubin, so I mean, these are things that Vera Rubin's doing, and the volume of data is immense. Excuse me. But they're trying to create a 10-year movie of the cosmos in 4 dimensions. So, distance from Earth, X and Y, and Z being the distance from Earth, and then also time. Uh, 20 terabytes, up to 10 million alerts per night for events like supernova, asteroids, active galactic nebula. There were 800,000 alerts on the very first night. We are now up to um, over a million, and that will ramp up. And the target is 7 to 8 million, but it might go as high as 10. And scientists have access to it. Excuse me, my cough is catching up with me. It started the full 10-year science operations, and it's run by the U.S. National Science Foundation and the Department of Energy's Office of Science. And it issued, as I said, 800,000 alerts on February 24th. It's now increased to over a million. And this is a big deal. And, as the months go on, we're going to start to see a lot of images. We're going to start to see a lot of data. And the number of discoveries are going to be immense. It's a great time to be an astronomer, really. It really is.
And when you have that sheer volume of data, this is where AI can really shine, because you can give it some very broad parameters of what to pick out and then send to someone who can evaluate it more clearly. I mean, that's the ultimate task for AI, is it can just churn through data so much faster than human can once you train it. I mean, it takes a while to train it, but if you're looking, you can send it through the data to look for galaxies. You can send it to look through for a supernova. You can send it to look through asteroids, because there's just so much data. There's no way humans could review all of this. But this is sort of ultimately the kind of task AI just excels at, is like churning through these massive amounts of data to find these trends or these particular characteristics that there's no way you could get through as is just using humans to do it, right?
It's exactly right. And of course, you couldn't, first of all, you couldn't process that amount of information, and you can't prioritize that amount of information.
Yeah.
AI is really going to be very good at not only processing the information, but also say, these are the things that must be dealt with first. Okay. And like supernova and asteroids might be two candidates there, but this is it's incredible technology. It's aggressive optical design. It is an incredible imaging system. Amazing data pipelines. It's got its own dedicated fiber optic network from Chile, fiber optic connection, I think, with redundancy from Chile all the way up to the continental US. And then, it's just, they've done everything right with this. It took a long time. I remember talking about this to some people I knew 15 years ago, and I'm finally here to see it. And I may even get to work on some of the data one day. It's just amazing.
Oh, it's a phenomenal size of project, but there has been a lot of thought and design that has gone into it. I mean, it's the telescope is the center of it, but it's all the data analysis and data storage and programming and all this other thinking around it, like the infrastructure, like you say, dedicated data lines that are what are going to make this project amazing, right?
Yep.
I mean, in a lot of missions, they've generated so much data, they don't even know what to do with all of it. It's still sitting there until someone gets to analyze it. But as this comes in and they can train the AI to look for supernovas and all the other kinds of things, it's just, I think it's going to be phenomenal when you're going to pull it. But you still got to bring in a human observer to look at these things in detail, because the AI can flag a whole lot of stuff, but that's just sort of step one, and sort of cutting through all the data to find, like, these are the interesting things, that this is what this person wants to see, this is what this person wants to see, this is what this person wants to see. I mean, it's not like the early days of SETI at home, if you remember that. They had to
Yeah,
parcel out all those things because SETI had so much data they couldn't process it all.
yeah, yeah. It's
So here
incredible.
they've actually planned to deal with that, which I find just a fascinating kind of approach to the science. It's sort of totally different from, well, even what we've had to do before, right?
I remember years ago, I used to think a gigabyte hard drive or a 10 gigabyte hard drive was a big deal. I've currently I've got 24 gig at home. I'm finding I'm doubling it every year or so. But that's the amount. Sorry, not gig. 24 terabytes. I've actually got 28 terabytes, and that is the amount of data that Vera Rubin will produce in just over one night.
Yeah, it's just the
It's
sheer amount, the
incredible.
sheer volume is
Yeah,
just
I know.
it's
I
amazing.
know. Yeah.
Um, but it's like I
So,
said, it's just you keep pushing more and more and more data, but then you get more and more detail. I mean, my research and stuff is in geophysics, and they're in the same situation where you're just getting such massive amounts of data. Um, and then you need to process it all, and then you have to sort of figure out what the hell am I actually looking at.
yeah.
Um, so
So,
that's where I think AI is going to shine in science, that it sort of allows us to narrow down to sort of specific things we want to look for.
but Mary Helen, closer to Earth, rather than what Vera Rubin's looking at, you've got some update on possible northern
Yeah,
lights.
so the British Geological Society, they have a geomagnetic observatory, and they have sent out a notice of a likely coronal mass ejection, which is basically a huge chunk of ionized material, should hit Earth sometime in the next 24 hours. And this is followed up with a strong solar wind from a coronal hole. So over the next few days, particularly if you look at Toronto, maybe a little too far south, but if you go a little north of here, there's a very good chance you will see northern lights. So if you go to, of course, NOAA has their Aurora tracker, which is lots of fun. It shows the sort of edge of it is a little bit north of Toronto in the area, but if someone was up in sort of the Muskokas or even a little farther north, there's a good chance, if the weather is clear over the next few days, you may be able to see northern lights. And the British Geological Society, they're talking about, people up in the Faroe Islands and Scotland and Wales and all these places are likely to see sort of Northern Ireland. Keep your eyes out for northern lights, but that's a little further north than we are. I mean, this storm is sort of right on the edge of being able to get visible in this part of the world, but our ability to, or our opportunity to see northern lights is probably going to continue to decline over the next couple of years, and then disappear as we're sort of on the downside of the solar cycle, and the number and the activity is sort of on the downside of the cycle, where it's sort of slowly getting less and less. Which, if you want to see northern lights, is bad. If you're someone like me who does geomagnetics, you're kind of relieved, because these things can really mess with your data.
Yes, it's when you get the chance to see northern lights, it's marvelous. I've actually been up, and I lived in Norway for a while, in the Canadian Arctic for a while, and it's a remarkable experience. Unfortunately, we just don't get it down here, and of course, with all the light pollution in the GTA, even if we do get it, it's difficult to make out. But certainly worth it. And yeah, we're past solar peak, and we're heading into, over the next 6 years, 5 years, we'll head down to solar minima, and that will mean fewer and fewer opportunities to see it. But it's good to know that we've got the ability to predict it, and if there is an opportunity, I'll be the first person there with my camera. It is really a sight to see. So we are actually coming up on time. So I guess I'm going to close our podcast for this evening. I want to thank you for joining us, and I want to thank you for putting up with my raspy voice. Um, you have been listening to York University Astronomy and Astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Professor Mary Helen Armour and me, Paul Mackin. The podcast and past episodes are available wherever podcasts are distributed. You can always connect with us on Instagram at YorkU Observatory or on Facebook at Allan I Carswell OBS. Our website is yorku.ca/science/observatory, and there is a lot of interesting content there. And if you feel so inclined, it's a great place to make a Canadian tax-deductible donation to our student-operated not-for-profit observatory. I want to thank you for tuning in this evening. We wish you clear skies and a great night, and start to enjoy the good spring weather as it comes in. Good night, everyone.
Good night and happy Easter, all.
Happy Easter. Yes. Yes, absolutely. Happy Easter. Take care. Bye-bye.
All right, bye.